Greetings, welcome back. So today we're going to be talking about heating chemicals a little bit. We'll focus on a chemical that's easy to heat and think about, water. This is kind of a weird thing because with heating, we usually in our everyday lives, we just apply more when we want more and we take some away when we want less. For example, if you're cooking something, meat, and it's not done, you apply more heat until it looks like it's going to taste good. If the room isn't warm enough, you just apply more heat until it feels good. And then vice versa, if you're trying to cool something down. You just take heat away one way or another, open a window, turn on the air conditioning until you've removed enough heat until you're satisfied. And so we know a lot about taking away heat and putting heat in. We do it every day. We spend a lot of our time doing it. Spend a lot of our money on it. Um, but we don't usually put a value on it, but it's super important to be able to do this moving forward. A lot of engineers in the class might end up taking a whole course called thermodynamics, which is all about figuring out where all of the little heat is going and adding it up and keeping track of every little piece of heat. And so this section is sort of the start of that discussion. It turns out that if one thing releases heat and say two things absorb that heat, you can add the heat up. You can figure out, okay, how much did object A absorb and how much did object B absorb? And then you add those together. That's how much total heat object A released. And so that was probably pretty obvious once you think about it. But again, we don't really think about putting values on heat, but you can just add up all of the different heat values to figure out the total. And so we're going to apply this to you already have a little bit of familiarity with this with changing temperature. So if you have a chemical, water, or a piece of aluminum, and it just changes temperature, do you remember what equation to use? Q equals mc delta T. So Q is the amount of heat, M is the mass, C is the specific heat capacity. That was different for every type of chemical. Water was 4.184 joules per gram per degree Celsius. A lot of metals are a lot lower. Water is one of the higher ones. And then delta T is the change in temperature. That was probably the first time you saw that delta, which we're going to use a lot this semester. Delta, final minus initial. So that worked if the chemical was undergoing some sort of temperature change, either warming or cooling, but it was very limited to no phase change, no reaction. So you can't then like throw in a piece of metal like sodium into the water and turn the water into hydrogen and oxygen gas. That's a chemical reaction. There is a lot of heat exchanged. For that, you'd have to use the enthalpy change. But you can't just use Q equals mc delta T. And what about if you're just warming up, say, ice? Say you put a piece of ice in a pan on a really hot stove. Well, first that ice is going to warm up to 0, and then it starts to melt. Now it's in the liquid phase. Then you warm that water up from 0 to 100 Celsius. Now it starts to boil. Maybe during that whole time it was actually evaporating a little bit, but now it starts to boil. And now it's all in the gas phase. Technically, if it's on the stove, it's just now in the room and it's cooling back down and it's condensing in different places maybe. But if it was in a closed container, you could then heat that gas. And so you got two phase changes, and we just finished talking about how during phase changes the temperature isn't changing. You're putting in a lot of heat to get to the water to melt, but it's not undergoing any temperature change. So you can't just use Q equals mc delta T. So now what happens if you want to figure out the total amount of heat that you've applied to turn a chunk of ice into steam? That's the problem we're going to work on here. The process is very similar for a lot of different chemicals. And so, yeah, we're going to do it for water, which again, we all have familiarity with. But as long as you know melting point, boiling point, heat of vaporization, heat of fusion, and then specific heat capacities for solids, liquids, and gas, you got those variables that you can figure out how much heat it takes to either heat or cool a chunk of matter, any chemical, from one temperature to another temperature, or cool it. So that would just be the reverse, which I might mention at the very end here. So here's a really cool figure from your book. So again, we're taking ice. So here's the main question that we're working on. How much heat does it take to heat 18 grams of water from negative 25 Celsius to 125? So we're starting down here and we're ending up here. We're kind of going this way, and then you got heat added there. So hopefully we get a number that's pretty close to 55, 56 kilojoules. And we're seeing like 5 different lines. And so again, at the beginning, you're starting with ice, and that first little bit of heat that you put in is just warming the ice. But then it gets up to 0, and this is again at 1 atmosphere near sea level. Gets up to 0. Now you're still putting heat in, but it starts to melt. All that energy you go in is breaking the hydrogen bonds that are holding it in the solid phase. So you got the melting point, and so now you just got ice melting. And so at the very beginning, you have 100% ice, and at the very end, you have 100% water. And everywhere in between, you have some mixture of ice and water, but the whole thing is still at 0. So you're putting heat in to maybe the water, but as the ice melts, it's absorbing that heat and it's keeping it at 0. So whenever you got ice in a beverage, the whole thing is at 0 Celsius. And now it's at 100% liquid water. And so now you're warming water. And we know every time that we're just warming a chemical, no phase change, no chemical reaction, we can use a Q equals MC delta T. So we're going to use a different Q equals MC delta T equation for this line. And you notice that those lines have different slopes, and it's because the specific heat capacity is very different. Specific heat capacity of ice and water and steam is just a little bit different, even though it is 4 grams. It's per gram, so you might expect that they would be similar. And now you get up to 100. Now you're still putting heat in, but it's not going to warm the liquid water anymore. Now it's starting to boil. On average, every single molecule has enough energy to enter the gas phase. And so liquid is boiling. And again, over at the beginning, you have 100% water, and at the end, you have 100% steam. You might imagine that this is in a closed container because we're going to keep heating the steam after too. And now all of it's in the gas phase, and you're still putting heat in. Now you got matter in a different phase, and it's at the lowest it could possibly be, and you're now it's starting to warm again. So this is steam warming, and this is going to be another Q equals MC delta T. And so that's sort of maybe the first bullet point that, or star thing I wanted us to notice here, is that solids, liquids, and gases have different specific heat capacities. You might be wondering, well, how are we going to calculate how much heat is exchanged during the phase changes? So again, the flat parts are the phase changes, and that's going to equal the enthalpy. This one is the vaporization. Our heats of vaporization were in per mole, so it's going to be times N, a number of moles. And the same thing down here. The heat, this is the heat of enthalpy of fusion. And again, our enthalpies of fusion, they could be in kilojoules per gram, but the ones in our textbook are given to us in kilojoules per mole. So that would be for 1 mole, and we're going to multiply by N, the number of moles. Okay. So we got 5 different curves, we got 5 different equations, and it turns out that the total heat is just going to be the sum of all those individual ones. So this is how you figure out the heat exchange when there's both warming and phase changes. You just add them up. Again, we're excluding no chemical reaction. So there's no chemical reaction. We don't have to worry about the water turning into hydrogen and oxygen. We're not heating it that high. So Q total will equal Q1 plus Q2. Q1 is the ice warming. Q2 is the ice melting. Q3 is the water warming, Q4 is the water boiling, and Q5 is the gas warming. And so Q1, we said it was an MC delta T. And so the mass of water is 18 grams. The specific heat, this is ice. So this is the specific heat capacity of ice. And it says that the specific heat capacity of ice is 2.09 joules per gram per degree Celsius. And then delta T, T final minus T initial. T final, that's what the temperature gets to. It started at negative 25 and gets up to 0 before it starts to melt. So T final is 0 minus a negative 25. So minus the negative, that delta T is 25. So 25 times 2.09 times 18. So you get 940.5 joules. This is going to end up being a lot of heat, and this is the smallest little chunk, or maybe the second smallest little chunk. But we're going to need to have this in kilojoules. And so I'll show it one time, but hopefully you're feeling pretty comfortable on conversions from joules to kilojoules. So 1 kilojoule is 1,000 joules. You move the decimal point over. So this is 0.94. They're calling it 1. I don't know if it makes a lot of sense to round too early here. 9405 kilojoules. So that's Q1. Q2. So now all of our ice is at 0, and now we're starting to melt it. And again, it's called enthalpy of fusion because they imagined crystals as they were melting, fusing together to make one droplet of liquid. It's sort of not intuitive, at least in my book. So we got to use the enthalpy of fusion. You got to remember vaporization is from liquid to gas. Fusion is from solid to liquid. And this is times the number of moles. So this is kind of weird because on the temperature changes, we're just using masses, MC delta T. But on the phase changes, we're using moles. And it doesn't have to be like that. Again, enthalpies could be in kilojoules per gram. Ours are given in kilojoules per mole. So we know that the enthalpy of fusion is 6.02 kilojoules per mole. And then this amount of water has been chosen to be exactly 1 mole, right? Because H2O, 2 H's, 1 O, oxygen's 16, hydrogen is 2, each hydrogen is 1.008, so this is 2.016. So they've kind of just rounded, technically it's that, but with only 3 sig figs, you call it 18.0. So that grams per mole, this is 1 mole, right? If you take 18 grams and you use 18.016 grams in 1 mole, those 18s cancel, and you got 1 mole of water here. So you could picture 18 grams, but then we also know, oh, that's 1 mole. And of course, you guys know 1 mole is Avogadro's number. So if you wanted to, you can imagine Avogadro's number of water molecules originally stuck in the ice, but now converted to liquid. Now all of it's in the liquid phase, but it's still at 0, and now we're going to warm it. So whenever you got warming, that's another MC delta T. But now this is liquid water. So you still got 18 grams of water. Now the specific heat capacity is very different. Joules per gram per degree Celsius. Delta T for this liquid water. Again, we're kind of going from left to right. It started at 0, and you can read that over there, and it ends at 100, the standard melting and boiling point of water. So T final, 100 Celsius minus 0. Because it's delta T, you can actually use either Celsius or Kelvin, right? Because if it was Kelvin, it would be 373 minus 273. The delta T would still be 100. So you take 100 times 4.184 times 18, and you get 7,531. This is still in joules, so we want to convert to kilojoules again. We already showed that conversion up here, but we're doing it again. So you get 7.5312 kilojoules. So that's Q3. We're going to end up adding all these together. Now all of your ice is actually liquid water at 100. You're still putting heat in. Now it's starting to boil. This was where the bulk of the energy, you probably noticed that we're around 14 or so, a little over 14, and kilojoules total. And this is going to get us up to about 55. So this is about 40 kilojoules of energy, again, because it's 1 mole. And that's the bulk of the energy. So this shows you how important boiling is. And this is where we spend a lot of our energy. So boiling, phase change, that's a delta H, that's an enthalpy, but this time it's a vaporization times the number of moles. So again, this is a constant that you could go look up. This is sort of another hint I'll give. So for water, we're getting familiar with these different constants, but if it was a different chemical, these are constants that we could go look up. We can look up enthalpies of vaporization or enthalpies of fusion or specific heat capacity of a solid or the liquid or the gas or the boiling point or the melting point. These are common things that have been studied for a long time, and they're sort of just literature values for a lot of chemicals. You have some tables in the back of your book that you can go look them up. The internet can be a good place to find a lot of these too. A lot of them get kind of summarized in that information page on the right on Wikipedia. So the enthalpy of vaporization for water is 40.7 kilojoules per mole. And again, we're still working with just that 1 mole. So this is going to be that 40.7. This problem might be a little bit more interesting to carry through if it wasn't exactly 18. You know, if it was something like 72 grams, well, we would have had to convert that 72 grams to moles, and then we would have used that number for N. So moles is the number of the sample that you're working with. And again, we just happen to be working with 1 mole in this scenario. And then question 5, heat 5. We've now got all of our water in the gas phase, and now we're still going to heat it up. We're now going to, but it's already in the gas phase, so we're going to warm our gas. If you're warming a chemical and it's in one phase, that's another MC delta T, but now the C is for steam, or the gas phase version of water. You still got your 18 grams of water. The specific heat capacity for steam is 2.01 joules per gram per degree Celsius. And something that I haven't pointed out yet, but the specific heat capacity is per gram per degree Celsius. So grams go away and your Celsius goes away. So that's why you're left with just joules at the end, which is what Q's come out in. Q's, heat, should always come out as joules or kilojoules. So this looks like it's going to be very close to 36, 2.01. Oh, whoops. And then times delta T. We starting at minus 100, and the question just said that we were going up to 125. Yeah, you can heat steam up beyond 125, but we're just wondering about that last 25 degrees there. So T final minus T initial. So there's another 25 there. So 25 times 2.01 times 18. So this is 904.5 joules, which is 0.9045 kilojoules. And now to get the total, we add up all of our Qs here. I got Q1, Q2, Q3, Q4, Q5. So let's divide this by 1,000. Use that. Plus 40.7 plus 7.5312 plus 6.02 plus 0.9405. So I got 56.02 096. Oops. 56.0962 kilojoules. Our delta T's kind of limited our sig figs here. We had 3 almost everywhere else. Probably a good idea to use 3. So we'll call it 56.1 kilojoules. Technically, here with subtraction, you've only got 2 sig figs. So you could have just called that 56 kilojoules. I don't see them actually add it all together, but that's about where we were expecting it to be. Okay, so these problems, when you see them, they can take on a couple different interesting formats. The first thing is that you got to remember what the graph looks like in order to sort of use this problem-solving technique. You got to remember that you got heat added on the X, and you got to remember that you have temp on the Y. And then you should remember that it's 5 lines, and it starts with the solid warming. So it starts up, melting, liquid warming, boiling, gas warming. So up, flat, up. Those are the 5 stages all matter will go through, unless, of course, maybe it's subliming or coming back fusing. Then this temperature over here, this corresponds to the melting point. So again, we use 0 because that was water, but different chemical will have a different melting point. This line up here corresponds to the boiling point. That will be different for every different chemical. And then a lot of questions won't have you go through all 5 stages. Maybe it's for water, it would be take water at 20 room temperature and cool it to -3, something like that. So we would have to know on this graph, we're actually not going to use any of the gas stuff. The question said you're starting at 20, so that's right in here, that's room temperature, and you're cooling to -3. So 1, 2, 3. So that would mean you need a Q1, a Q2, and a Q3. Each one should be negative, right? So that's another thing here is that for cooling, each Q should be negative. That means you're removing the heat from the object. And that's because freezing is a negative change in enthalpy of fusion, and condensation is a negative enthalpy vaporization. And for the phase change, the temperature changes, delta T, if you're going cooler, the example I just used was you start at 20 and you cool to 0 first if it was water. So the delta T would be final minus 20. So it comes out to -20. That's where the Q. And so thus, Q will also be negative. So both phase changes will be negative, and all 3 temperature changes will be negative. And then when you add them together, you get a net negative. So, look out for that. Yeah, so if you remember the shape of the curve, you remember to put your melting point, your boiling point specific to the chemical in. And then when you're looking at the question, if it says, cool from -20 from +20 to -3, I like to have the graph there and say, oh, I'm starting here and I'm going to there. That's a Q1, a Q2, a Q3. Obviously, we don't need the boiling and then heating the gas because it started as a liquid and we then froze it all and then cooled it a little bit below the freezing point. And so that's using all of these constants to think about the total heat exchange, not just for warming or cooling, but also moving through phase changes. And I hope you feel a little more comfortable finding the total heat exchange when we're doing both at the same time, when we're warming or cooling, and causing phase changes.